Good morning. Today we're talking about Chapter 9. It's called Statics. Statics is very simple, very easy to understand. It means that nothing is moving. Okay? Here are some objects that we build that we want to be static, that we want to stay in the same place. Right here, if you build a big old building, you want it to stay there, right? And you don't want it to move. If you sit on a chair, if you have a bridge, right, these things we want to put in place, we want them to stay there. Here's a picture of a crane. Yes, a crane moves, but I want it to support the weight and to be able to stay where it is and not get pulled over by whatever load is placed on it. So I've put that picture in there as well. Static means it's not moving. So this is kind of like what we did back in chapter 4 and 5 with the sum of the forces, except this time nothing accelerates, nothing moves. It's a much easier problem that way. The first rule of statics is very simple right here. If I don't want something to move, then the sum of the forces on that something better be equal to 0. And right here you can see that I've got this box right here, and there's a force this way which we've called F1. There's a force this way which is F2, and again, if this force 1, is the same as this force F2, then those are going to cancel out and I don't get any net force on the thing, therefore I don't have any acceleration, and if it's at rest originally, then it will stay at rest and therefore be static, which is the goal of all this. You can break it out into all three directions. You could say the sum of the forces in the x direction equals 0. That's kind of what we've represented here, but you can see how the sum of the forces in the y direction also need to cancel out, as well as forces in some kind of other z direction, third dimension here. Hard to draw on a flat piece of paper, but the sum of the forces needs to equal 0. Sometimes, you need to say, yes, I've checked it off in the x direction, the y direction. Could even do it in the z direction. We probably won't do it in here, but if you've got those first two done, and maybe the third one, then that thing is not going to move. Let me show you an example. This is what we call the hanging mass problem. And over here you can see that there's a stoplight right here. That stoplight is suspended by a cable, and then another cable goes this way and another cable goes that way. So what we need to do here would be to do this type of problem, which again I'm calling the hanging mass problem, is to follow the steps that are on the side there. And we've done this back in chapter 4, except there it was more complicated because it's moving. But I need to draw the three forces. So I'm going to come in here and draw T1. I'm thinking about this point right here, right? That's the point where all of those forces come together. And let me just draw in the forces there, and let's just see what I'm talking about. I have T1, this cable pulls in that direction, right? On that yellow point right there, the cable is pulling up and to the left. Meanwhile, T2 is pulling this way. It's to the right and up. And so I draw in those two forces. There's one more force here that I need to include in my picture. The weight of the stoplight itself pulls down. So I've got those three forces that are acting on that point. Again, this is the point of interest right there. I want to make sure that that point doesn't move, which is really to say that the stoplight doesn't move, right? But this point up here is where all of my forces come together. I want to think about that point and the forces on that point. And so the first step here was to draw the forces, T1, T2, mg. We have done that. We'll label them here just to make everything happy. This again is T1, tension number 1. Over here is T number 2, and then right here I've got the weight mg acting down. The next step is to do what we said, right? We need to sum the forces in the x direction, and then we need to sum the forces in the y direction. I've done this on the next screen already, so I'll show you how that works. But as soon as I have those two equations built, then all I have to do is to solve simultaneously. And so it's a really nice, easy way to approach a problem like this. Say I want it to be static, therefore I need to make sure that it doesn't move in the x direction, it doesn't move in the y direction, and those equations lead to the solution. Here's what I've got for you on this one. Same problem here. The only thing that I've added is the mass of this thing. So the mass of the stoplight here is 20 kilograms. And again, we're thinking about this point right there. I've got three forces. This cable pulls up. That angle is a 37-degree angle. And remember your geometry here. If this angle up here is a 37, then this also has to be a 37. That would be here are two parallel lines that are cut by a transversal. Remember that? So this angle, that angle are the same. Similarly over here, this would have to be a 53-degree angle because the angle up here 53. Okay, so what we've done is we've got the three forces. Tension 1 pulls this way, which is really to the left and up. So I've gone ahead and broken those down. T1x, how hard does it pull to the left? Well, it'd be equal to the tension in that cable times the cosine of 37. Cosine because it's the adjacent to the angle of interest. Over here, the opposite would be equal to T1 sine 37. So we've got that labeled. We can do the same thing for the blue arrow here. T2 pulls to the right. T2 cosine 53 degrees. That would be the adjacent to that 53-degree angle. So I've got the hypotenuse and the adjacent, which makes me think of cosine. And then lastly, right here, it's pulling up. That would be the opposite. T1, that should say T2 right there, typo, sine 53. Okay. The third arrow then, right there, the yellow one, the one that's kind of hard to see, is the mass, or the weight of the stoplight rather, and the mass is 20 kilograms. So if I take 20 kilograms and multiply by g, then I've got my weight right there. Okay, let's build our equations. Remember, we had 3 steps on these. First step was draw the forces. Okay, we have done that. The second step was to build this equation right here. Sum of the forces in the x direction equals 0. So I go back to my picture. I'm looking for forces that act in the x direction. I can see that T1 has an x component. I can see T2 has an x component. So I need to get this thing and this thing. Those are the only 2 forces that act in the x direction. The weight is solely up and down. That's in the y direction. We'll get to that in a little bit. But right here, T1 cosine 37, it pulls to the left. So I've put that over here, and that left, I've marked that it pulls to the left with a negative sign. I'm thinking about a coordinate system that looks like this. My x coordinate system is positive to the right, negative to the left. So when T1 pulls to the left, then I put a negative sign in. Right there. T2 pulls to the right, so I've got a positive sign to indicate that the red arrow pulls to the left, the blue arrow pulls to the right, and there's my equation right there. T1 cosine 37 is this piece pulling left. The T2 cosine 53 pulls to the right. Just to simplify, that cosine 37 is equal to about 0.799. So I've gotten a decimal approximation for the cosine of 37 and also 53. Just makes it look a little bit better. It's not quite as scary. It's just a number. Just make it a number. Okay. Once I have that equation built, then I need to build the other equation right here. And there's my starting place right there. Sum of the forces in the y direction equals 0. This time I'm looking for forces that are pulling up or down. T1 pulls up, so that's a T1 sine 37. I've got it right there, sine 37 T1. And then T2 pulls up. That was, again, that should be a T2 right there. But T2 cosine 53, I've got that. The weight pulls down, and see how we've got a negative sign right there to indicate I've got positive, positive, negative, because it's up, up, down. And that would be the equation that I need to put down on my piece of paper. We can put in the mass, 20 kilograms multiplied by G, 9.8 right there. And this is the equation that we're interested in solving there. And those two can very easily be solved simultaneously. I think we can probably do that right here. Let's go to another page. I'll have to flip back and forth and write this down, I guess. But we had negative, where's my pen? Negative 0.799 T1 plus, let me get the number here, 602 T2, and that's equal to 0. The other one was 0.602 T1 plus 0.799 T2 minus the 196 newtons, and that was equal to 0. So those are the two equations that I want to solve. Some of you may be interested in why it's 0.602 and 0.602, 0.799, 799. That's mostly because the two angles involved here were complementary angles, and so the cosine of one angle is equal to the sine of its supplement, or its complement. Okay, that's all that's happening there. Don't worry about that. So I want to solve these simultaneously, and we'll do that right here. I'm going to take this first equation and solve for one of the variables. We're going to do a substitution method here. Let's solve for T1, I guess. T2 maybe. I don't want to deal with that negative sign. So if I've got 0.602 T2 and I add the other term to both sides, then it would look like this. If I divide through by 0.602, then I'd have 0.799 T1 divided by 0.602. And when I do the calculator work, lost my calculator. Oh, it's a sad day. Here it is. 0.799 divided by 0.602, 1.33. Okay, and now I know what T2 is in terms of T1. So if I take this thing and I substitute that in for T2 right there, and we'll build the other equation, or rather take this one, the second equation, 0.602 T1 plus 0.799 T2, but here's where we know what T2 is worth, and I just make that substitution right there. Again, just came in right there. 196 equals 0, and now you can see that I only have one unknown, so we can solve this with no real trouble. 1.33 times 0.799, 0.602 T1 right here. I would have a 1.06 T1. I'm going to go ahead and put the 196 on the right hand side, adding that to both sides, and then I would have 1.662 T1 equals 196, and if I take the 196 divided by 1.662, then T1 has to hold 118 newtons, and knowing that, I can bring it up here, and we had that T2 was equal to 1.33 T1, so that would be 1.33 T1 we found to be 118 newtons, and that comes up about 157 newtons. Okay? Those are the strengths that those cables have to hold. Otherwise the thing falls. Otherwise the thing breaks, right? Now if we take those numbers back, 118 and 157, to our picture here, let's just kind of close the loop on this. 115, is that what I said? I can't remember anything. 118 and 157. 118 newtons right there, and 157 newtons for T2. You'll notice that T2 has to hold more of the load than T1 does. That's kind of interesting. It's not terribly surprising when you think about it, though, because you see how this angle is bigger than that angle, and the steeper the angle is, then the more the load that it holds. And so that's kind of what we would expect to see there. If I wanted them to have exactly the same amount of load on them, then I would need to make these two angles the same. All right. One other interesting thing here that we could point out while we're right here, if I add those two tensions, 118 plus 157, I get 275 newtons. So that's kind of an interesting number in that, remember, we were only trying to hold up 196 newtons. My stoplight only has a weight of 196, but when I put those cables at angles like that, then they also have to pull against each other. The red arrow and the blue arrow, there's some extra tension in there because of those X components. And when this guy pulls left and this guy pulls right, those forces have to cancel out. The Y direction forces here, those still have to hold the weight. So this plus this would be that 196. But when I put in these X components, then I get a tension 1 and a tension 2 that add to more than the weight of the stoplight. So that's how you do a hanging mass problem. It doesn't really have to be a hanging mass problem. It could be any kind of object. If I have an object right here and I'm looking down on this object and I have various forces that are acting on the object, you know, maybe this is a Aunt Bertie's chair, and everybody in the family loves that chair, and Paul is pulling this way on it, and Tim wants the chair, and so he's pulling, and Aunt Sue is over here fighting over it and something. They're all pulling, but they're canceling out. That's a statics problem, right? If it's not moving, whatever's going on here, if you can arrange those forces, sum the forces in the X direction, set it equal to 0, sum the forces in the Y direction, set it equal to 0, then I just generally call that a hanging mass problem, and that's one of the types of problems in Chapter 9. There are only 2 types of problems in Chapter 9. That's one of them right there. And you can see it's not that bad. All right, let's look at the other kind. First, we need to define something called torque. Torque here is what causes rotation. And if you think about a wrench, here's the nut. We're trying to loosen this thing up. We put a big old wrench on it like that, and we're going to pull on it. You can see that here we're pulling down, or I could reach way over here and pull down, and you probably know that I get different amounts of rotation, different forces on that nut if I hold my hand at point A or at point B here. The farther it is out to where I apply that force, then the more torque I get. Torque is force applied at a distance from a point of rotation. This would be the point of rotation, and I'm applying force out here at some distance like that. So if I come in here and calculate these 2 torques, what they've written here is force of 20 pounds at a distance of 1 foot. So if I write the torque of A, that would be the force that I apply at point A times the distance to point A. Torque equals force times distance. That's assuming that the force and the moment arm there, the distance, are perpendicular to each other, and that's what we see right here. My moment arm runs this way, my force runs perpendicular to that, and so that's all we need to do here. In this case, we had 20 pounds, 1 foot, and you can see that would be 20 foot-pounds. okay, of torque that I would have if I pulled it 1 foot with 20 pounds. If I do the same thing with B, from the point of rotation out here to B, my radius is 2 feet, but notice they've got 10 pounds of force out there, so the torque from force B there would be force B times distance B, and that would be in this case 10 pounds times 2 feet. So even though I'm pulling with half of the force, I still have the same amount of torque. Okay? Torque causes rotation. Torque is force applied at a distance from a point of rotation. You need to know how hard you're pulling and where you're pulling. Same thing happens with a door. Let's say that this is a door that we're looking down on, right? Here's the hinge of the door. If I try to pull open a door halfway, between the hinge and the doorknob, that's pretty hard going. That takes a lot of force. If, on the other hand, I pull out here at the end of the door, that's pretty easy to rotate. So try that sometime if you need to put your hand on something and see what it feels like. All right. The second rule of statics then, and remember again, the first rule was that the sum of the forces have to equal 0. But the second rule would be that second rule is this guy right here. The torques also need to cancel out. The torques have to cancel out. If I have a door, and here's the hinge, right? That's my point of rotation right there. Let's say that I'm trying to push the door open this way. So I've got some amount of force right there at some distance, R1, and you're trying to push the door the other way. F2 at some distance, R2 from the point of rotation. Then those, in order for the door to remain static, those two torques have to cancel out. Not the forces, but the torques. So I need to make sure that the sum of the torques equals 0, and my torque and your torque, we'll call those torque 1 and torque 2, have to equal 0. Notice that these are in opposite directions. If I come in here and draw a little coordinate system right here, I'm trying to rotate the door up, we'll say, in the positive direction, counterclockwise, whatever you want to call it. You're trying to rotate it clockwise, opposite direction, so that's a negative sign right there. That's the best way to get your coordinate system set up. Draw a little arc on one side. I always do the right hand side there, and then if it rotates it positive, if it rotates it counterclockwise, call it positive. Clockwise would be negative. And so you can see there, I'm trying to rotate this thing in the positive direction. You're trying to rotate it in the negative direction. And I've got a little equation, really easy to build, really easy to solve, like that. In the picture down here at the bottom, I've got a beam. And usually there's some kind of long, skinny object here. And so we call these beam problems. This one has 3 forces applied to it. The point of rotation is right there. So since that's my point of rotation, I need to find all of my distances from that point. F1 here, somebody's pulling on this beam and about this point, so I need to measure from here out to F1. We've called that D1. Force 1 acts at D1. Here is force 2 pulling down right here, and that's at a distance from the point of rotation D2, and force 3 is at a distance D3 right there. What we need to do though is to think about our directions, and again, if I come in here and I draw a little coordinate system, draw a little rotational coordinate system like that, some of these forces are trying to rotate it in the counterclockwise direction, some in the clockwise direction. Those are opposite, so one needs to be positive, one needs to be negative. Doesn't really matter which way you name it, just pick something and stick with it. Now the best way for me to do this is to physically take my pencil and hold it right there on top of the pivot point, on top, hold your pencil right here, and then with your fingers at that point, that is the point of rotation. So if you have your pencil right there and you're holding right there at the fulcrum at that little triangle, then you can see that force 1 over here, if I push down where force 1 is on my pencil, then the right hand end of my pencil is going to go in the positive direction. It's going to rotate counterclockwise, and we have called that positive. If I pull down where F2 is, and again I'm holding my pencil right there at that point, pull down where F2 is, then the right hand end of the beam is going to go down. The pencil rotates clockwise, and we've marked that negative, so this would be a negative force. Force 2 right here, if I were to pull down on this thing about this point right there, it would rotate in the negative direction, so that guy would get a negative sign. And that's all I have to do to set this up. On the next screen here we've done that, and here is the beam problem that we want to think about. Same beam, same force 1, 2, and 3. I've made up some numbers now. Force 1 is 20 newtons, force 2 is 10 newtons, force 3 is 8 newtons, and those that are distance 3 meters and 4 meters, D2 is unknown here. So we'd like to find out where I need to put this 10 Newton force to balance the stick so that it doesn't rotate, so that it stays static. 3 people pulling on it, we want everything to cancel out. So whenever I have a beam, a long skinny object with forces at different points along the beam, then I need to set up the sum of the torques equals 0. Here I've got 1, 2, 3, so I need 1, 2, 3 terms. These are torques that we're doing. Torque is force times distance, so I need F1 times D1. That'll be my first term. Here's force 2 times distance 2. That's the second term. The third force gives me the third torque, so this would be F3 times D3 would be torque 3 right there, and I've got 1, 2, 3 torques. Everything adds to 0 because nothing moves here. What we've done then is I've got some numbers mixed up here, don't I? I took this term right here and added it to both sides. So add F2D2 to both sides. This should say F2D2, and this one should say F3D3. So I've got a big tangle here. Subscripts are all goofed up. All right, let's write them like they should be. This one should be F3D3. This should be F2D2. Again, we added that to both sides. It came over here on the right hand side. Okay. Let's see what needs to get changed on the next line. Right there. I've got F1D1 minus F3D3, and then we divided both sides by F2. Actually here, leaving D2 by itself. That's what we're trying to solve for. That distance from here to there is D2. I don't know what that is. I want to find out what it is. Put in your numbers here. F2 is 20. F1 is 20 newtons times D1 is 3 meters. F3 is 8 newtons. D3 is that distance right there, 4 meters. And then I need to divide by F2. That was 10 newtons. So finally I got a line right here. When I do all that, I get 2.8 meters. Okay. If I have a 20 Newton force and a 10 and an 8, that makes 18. If I've got these distances, 3 meters and 4 meters fixed on those, then this needs to be 2.8 meters to balance this thing and make it static. Okay. So let's do one more of these since I kind of goofed that up here. Anything that's a long skinny line is a beam problem. There will be forces at various points on there. Doesn't matter where they are. Let's say F1 is 200 newtons, and then right here I have F2 is 60 newtons, and then over here I have some unknown force F2 equals question mark. Okay? If I can draw those 3 forces or 15 forces or 6,000 forces, whatever's going on with my beam, I put it down like that, and then that is the basis where I want to start for my problem. Okay, I have to know some distances, otherwise I can't calculate the torques. So we'll put in the distances here, but the trick is you have to know where you're measuring from. I have to pick a point. And it doesn't matter which point I pick. Well, sometimes it makes the math easier if you pick the right point, but I can pick anywhere that I want to, as long as I measure from that point. So let's pick let's say that we've got this point right there. Maybe this is a door. I'm looking down on a door here. I've got 3 people pushing on a door, and it's static. Maybe it's a bridge, right? And maybe I've got a truck parked right here, and I've got an elephant right here, and something's holding up in the middle, right? So actually I've got some numbers here that aren't going to work out, are they? Can I change that F2? Let's make this 600 newtons, okay? Sorry. So if I measure these distances here, then that's the second step. I need to measure all distances from the point of rotation, which was this point, right? So in this case, I'm going to just make up some numbers for that. We're going to say that R1, the distance from the point of rotation to force 1, is equal to 3 meters. R2, the distance from the point of rotation over here to this guy, is going to be 8 meters. And then I've got 2 2's on. Let's make that a 3. Here R3 is going to be 12 meters. Okay, that'd be the distance from the point of rotation all the way over there like that. Okay, so now I've got my numbers. The next step is always to sum the torques, set it equal to 0. So we do that, and because I have 1, 2, 3 forces, I'm going to have 3 torques. That would be F1 times R1, be F2 times R2, and F3 times R3. All of that's equal to 0. I do have to get my coordinate systems straightened out here and know whether I'm adding or subtracting these torques. Here again, I'd like you to physically hold your pencil on top of this, but your fingers are right there at the point of rotation. So I'm holding a pencil at one end right there, and then I'm going to pull down on it, and I'm going to push up on it, and I'm going to pull down on it. Those 3 forces will make it go in various directions. This guy, if I hold right there, my pencil runs over here, when I pull down, then it's going to go down. So I'm going to call this the negative direction, and F1, R1 would be a negative torque. It tries to rotate it in the clockwise direction. F2 lifts up. So if I'm holding my pencil at this point and I push up on it right there, then it's going to go upwards. And so I would call that torque positive. For the last one here, I'm pulling down. Again, I'm holding the pencil there. It runs over here. When I pull down right here, it's going to make the pencil, the right-hand end of the pencil, move down. So I would put a negative sign there. And I've got those 3 torques. I've got the coordinate system set up to do this. The thing that I was looking for again was force 3, this guy. So we'll solve for that. Let's add that term to both sides. I'd have negative F1 R1 plus F2 R2 equals F3 R3, and then I want to divide both sides by R3, and I'll get that. Here's negative 200 newtons times 3 meters plus 600 newtons at 8 meters, Want to divide all of that by what on earth? 12 meters. And that's going to be the force that I need to put right there. And I'll get you a number real quick here. Negative 200 times 3 plus 600 times 8. Close that up in parentheses, divide the whole thing by 12. I need 350 newtons right there to make this thing balance. Okay? That would keep it static. Everything that you do in statics is one of those two types of problems. It's either a suspended mass or it's a beam problem. And we'll do some more of these in recitation, but that's what we need to know how to do for Chapter 9. Thank you.